Okay guys, let's take a look at our lesson after our fun out in the cold. Okay, so our first lesson in this unit is on parametric equations, and the first thing that we're going to do actually is just to take care of some definitions. Definition of a plane curve. So f and g are continuous functions of t on an interval. And you probably recall this type of equations from last year. Parametrics is where we have a set of equations, an x equals and a y equal equation. They're both with respect to t. Those are called parametric equations, and t is called the parameter, which should be a review for us. So the set of points obtained as t varies over the interval is called the graph. Pretty common sense. Together, the graph and the equations together are called a plane curve. And so that's really the definition of a plane curve. It is the graph and equations of the parametrics. Those are a plane curve. So that's just some vocabulary stuff. All right, so let's take a look at our first problem. This, for the most part, should be a review to us, should be a little comforting after fairly difficult lessons recently. So let's take a look. If you'll recall from last year, basically it's a triple T chart. In this particular case, the equation itself limits our interval, our t interval. Sometimes the equation will limit it, like this one, where t can't be less than 1, right? 1 is the smallest t could be. And sometimes they will give us an interval, of t interval that we are looking at. So there are a couple of different ways, and then sometimes there's no restriction at all. You can use any t. In this particular case, we're restricted by the equation. And we can't really start with 0, so we're going to start with a 1. It is possible for t to be negative, and that's okay. It's okay for t to be negative. Get our x value of 0. Okay. Then putting a t value in here is a 3. And so forth. We'll do a 2. I'm actually going to do t values that are convenient. I don't want to try to graph the square root of 3, so I'm just going to do some convenient values. Put a 2 in here. The square root of 1 is 1. 2 in there would be a 4. The next t value I would do would be a 5, just because it's convenient, because the square root of 4 is 2, and then 5 plus 2 is 7. I think that's probably enough to give us an idea of what the graph looks like. So let's take a look. Let's graph this. So 0, 3, 1, 4, and 2, 7. Okay. We need to show a direction. And if there's not a restriction on continuing, let's say I can keep going. There's no restriction. I have to extend my graph out to my line, the plane curve, out to the end of the graph. Kind of keep that in mind, because some of us are going to be inclined on a line to try to put arrows on both ends, but that would not be appropriate, because these are one-way graphs. The parametrics go one way, and so we put one arrow is sufficient. Somewhere in the middle of it. You can put more than one arrow if you want to, but one arrow is sufficient. We just need to continue to go until we reach the edge of the graph, unless there's a restriction. Does that make sense? We have to finish out the graph. All right, so now let's eliminate the parameter. One technique on eliminating the parameter is to simply use substitution. We would solve one of these for t and sub into the other. In this particular case, I would solve this one for t. So t is going to be y minus 2. And then I would sub that into my first equation. So x is going to be y minus 2 minus 3. And cleaning that up, I get y, minus 1. Yeah, I get y minus 3. So here are the things that we need to consider on where to go from here. If this is the typical way one of these equations would be written, we could stop. If you look at the graph, that pretty much looks like half a parabola, and that's not how we write half of a parabola. So we would go ahead and solve for y. Okay? Normally you're going to solve for y. The exception to that is if you have a sideways parabola. One of those sideways parabolas, you know those equations are like x equals the y squared. You don't have to solve for y in that case. But in this case, that would typically, this equation would be a parabola. So we would square both sides and solve for y. Now, here is another consideration that we have to make, and that is when we get our equation, we have to decide if we need to layer on a restriction, if there is something additional that we need to add to this. If this graph right here, if this equation creates this graph without any kind of restrictions, we would leave it alone. But we know that if we were to graph this, not knowing any of our previous information, this would be a full parabola, wouldn't it? So we have to layer on another restriction so that if someone were to graph this, this is what they would get. They would get just this part of the parabola, this piece. So in this case, we're going to restrict the x. And again, we would restrict x or y. The t is no longer part of this equation. So our restriction is going to apply to the x or the y. And we're going to restrict the x here and force it to be larger than or equal to 0. And this whole part right here is the answer. In this particular case, you have to have a restriction. Okay? Is everybody okay with that? Okay. A couple more problems. Let's go to the next page. All right. So here we have another type. Get rid of this. Okay. Here we have x equals t squared minus 3 and y equals 2t. The thing that's different about this one is we actually do have some restrictions right here. Our t values have to exist starting at -2 and going to 3. So those are really the only options that we have. So we're going to do a t chart. We're going to start at -2. Now I'm working through all of them for my students that like to conserve energy. You have to at least do the first and the last and enough in the middle to know what it's supposed to look like. You know, I don't want you to draw in straight lines if there aren't any straight lines. So I'm just going to go ahead and do the whole sequence. It's not that many. It's not going to take that long. And I would substitute the -2 in here, and that would give me, what, a 1. Put the -2 in here, I get a -4. Substitute the -1 in here, I get a -2. -1 in here, I get a -2. Substitute the 0 in for t, I get a -3 and a 0 for the y. Substitute a 1 in, I get a -2 and a 2. Substitute the 2 in, 4, so I get a 1 and a 4. And the last one is substituting a 3 in, I get a 6 and a 6. Okay, so the order that these points are in is the order that the parametrics will travel. That's the direction that they're going to go in. They're going to start at 1, -4. Okay, so 1, -4, 1, 2, 3, 4, and then they're going to move to -2, 2, -2. Then they're going to -3, 0. And -2, +2, then 1, 4, and 6, 6. Okay, so it's moving this way, and so I would, put my arrow somewhere in the middle. If one arrow doesn't seem sufficient to you, you can draw more. In this case, we would not go out to the ends of the graph. I would not come back over here because it doesn't belong over there, and I would not go out here. This indicates a partial graph. And so I'm going to have to restrict that. I mean, you could probably see there's going to have to be some kind of a restriction here in order for us to get a shape that looks like this. So let's go ahead and work to eliminate the parameter. That means get rid of the t. So I would solve this one for t. So I get y over 2 equals t, and then I would sub it into the original. So x equals y over 2 squared minus 3, or x equals 1/4 y squared minus 3. Now this, if you look at this, it does look like a sideways parabola, and equations that are sideways parabola, this is a typical equation. It would look like that, right? It would have the y squared in it, it would have the x. So we really would not solve for y here. It would be one of the only instances, or one of the few instances where we don't solve for y. But we are going to have to provide a restriction, because this equation itself would fill out this whole graph. So the most convenient, or the easiest way to restrict this would be with the y's instead of the x's. Because if you'll notice, if I restricted the x's, the x goes from -3 to 6. But that would allow an opening for this piece to come in, and we don't want that to happen. So instead, let's restrict the y values so that the y values can't get lower than -4, and the y value can't get higher than 6. That would be a more appropriate restriction. So -4 less than equal to y less than equal to 6. And this whole thing would be my equation. Okay? The very last one deals with sine and cosine. And what I like to do on my t-chart is since we know it's just a regular period from 0 to 2 pi, I mean, that's what these look like, I try to get away with just doing the quadrantals. 0, pi over 2, pi, 3 pi over 2, 2 pi. That's what I try to get away with doing. And a lot of times it's enough. Sometimes it's not enough, and I have to insert other values like pi over 4 or something else. But I try to get away with getting a shape with just the quadrantals. And in this case, it's enough to work. So we substitute a 0 in for t. Cosine of 0 is 1, so that gives me a 5. We substitute a 0 in for t over here. Sine of 0 is 0, so it gives me a -1. Okay, pi over 2. Cosine at pi over 2 is 0, so that wipes this out. We're left with a 3. And sine at pi over 2 is 1, so that gives us a 2. Okay, we okay? I'm not going too fast, am I? These are just unit circle values. Looking at pi, cosine of pi is -1, so 3 minus 2, that gives me a 1. Sine of pi is 0, so that gives me a -1. At 3 pi over 2, cosine is 0, so that gives me a 3. And sine is -1, so that gives me -4. And 2 pi would be the same values as 0. So it would be 5. I get back to where I started. So let's go over here. We're going to start at 5, -1. Okay, then we're going to go to 3, 2. And then we're going to go to 1, -1. And then 3, -4. And then back to 5, -1. So we started here and we worked our way around this way. So we have an ellipse that's turning in that direction. And we want to eliminate the parameter. Now, the way we eliminate the parameter with ellipse is a little different than we did with circles last year. So just slightly different. Same concept, but we can't do it exactly the same way because these don't have the same coefficients. So I'm going to show you a different way to do that than perhaps you did it last year. What we're going to do is we're going to solve for cosine t and sine t. So I have 2 cosine t equals x minus 3. And then I divide by 2. And so I get cosine t equals x minus 3 over 2. I'm going to do the same thing over here with sine. So I get 3 sine t equals y plus 1. So sine t is going to equal y plus 1 divided by 3. Now what we're going to do is we're going to square. We're going to square both sides of each of the equations, and we're going to come up with a cosine squared and a sine squared. What do we know about cosine squared plus sine squared? What do they equal? 1. And so that's what we're going to do. We're going to basically square everything, and then we're going to set up a new equation and have x minus 3 squared over 4 plus y plus 1 quantity squared over 9 equals 1. Now this would be the equation of our ellipse, and it looks like a standard equation of ellipse. So that's how we would work it if our coefficients of these weren't the same. Okay? All right. Questions? Or let me turn this off.